Okay, let's continue. Let's continue. So I'm happy to present Team from also Apache Flink project and with artisans, and he's going to talk about Apache Flink streaming.
Yeah, thanks for the introduction. I'm Phil, I'm a Flink committer, and today I'm going to tell you a little bit about stateful stream processing with Apache Flink. So for those of you who haven't heard about Flink, it's an Apache top-level project since December 2014. By now it has become quite active with about 150 contributors working on the project. In a nutshell, Apache Flink is a parallel streaming data flow runtime with which you can do stream as well as batch processing. But in this talk, I will concentrate on the streaming part. The runtime is capable of giving you low latency as well as high throughput if you set the configuration right. It has a fault tolerance mechanism which gives you exactly one semantics, which is nice if you require the correct results. And it lets you do stateful operations, which we will see that is really useful later on in my talk. But before, let's quickly talk about stream processing and why it has become so popular these days. One of the reasons is that many of the problems we are facing now, for which we use batch systems, are actually a stream nature. So it would make sense to process the events of the data when it arrives, not batching it up, to process it at a later time. By doing so, you basically have faster results. You don't have to store all the data, and you have more predictable resource consumption in your cluster because they're constantly processing the incoming events. But since all theory is great, let's look at an example, and this example is going to accompany us for the rest of the talk. I want to count with you tweet impressions. So you have an input stream of events where each event signifies that a certain tweet has been fed to a feed. So, and now what you want to extract from this input stream is how often was maybe the blue tweet or the green tweet, how many impressions did it get over a given amount of time. So what you usually do, or how you would do it, is you have the input stream, you group according to the tweet, then you find a kind of time frame for computation, because the input stream can be theoretically infinite. And doing an infinite aggregation or computation will take you infinitely long. So you need some kind of, let's say, I want to know the impressions over the last hour. Okay. That's quite easy, I guess, the example. So how would we implement that with Apache Flink? Okay, first of all, we have to define the data type of our input stream. It can be any Java or Scala type. In this case, I've used the case class because they're so nice to sing. One field is the ID, which identifies the tweet. Then we have the timestamp when the event happened, and the count value, which will be used for summing up the impressions. Next, we have to get an execution environment. And in this case, it's a stream execution environment, which will tell Flink that we are executing a streaming job. Once we have that obtained, we can use it to read from a source. Flink supports various sources like Kafka, RabbitMQ, file sources, and many others. But here I've used my magic Twitter source to directly read from Twitter the impression events. And this will give us a data stream of tweets. Okay, now as we've obtained the tweets, we can start with the actual computation. The first step was, if you remember it correctly, to split the stream into the events for the individual tweets. And that was done in Flink by this keyBy method, which you give the field name of your type on which it shall group. Next, we define our time frame, and here, I set it to create a time window of 10 minutes, and within this time window, I will compute by calling sum the number of impressions I've received. Okay, that's the job. This gives us a new data stream where the tweet contains now the counts for the impressions the last 10 minutes. And in order to execute the program, you have to specify a sync. In our case, it's simply printing it out. And then we have to trigger the execution by calling execute. Okay, that was quite easy, I guess. But already at this simple example, you've seen an important concept of stream processing, which is we have to, for aggregations, we have to define a time frame, or what we call the window. Flink comes with different notions for windows. The simplest one is the tumbling window, which is basically a contiguous, non-overlapping window. So it splits up your input stream into segments of 4 elements, in this case. And on these 4 elements, you can, for example, do the aggregation of summing it up, which will give you, in this case, 27, here 22, and 8. Slightly more powerful window is the sliding window, which allows you to have overlapping windows. So by defining a sliding window of length 4, so contains again 4 elements, with a slide length of 2, which basically says that the first 2 elements of each window are overlapping with the last 2 elements of the preceding window. You have a different window semantics, which lets you do different things. Here in our example, the window length depends on the size, on the number of elements. But you could also define it depending on the time. And for time, Flink supports processing time, which means the time when an element arrives at an operator, as well as event time, which means the time when an event was created. This is really powerful because this means that we can handle out of order elements. So if you read, for example, from multiple sources, it's not sure that all elements will arrive in order. And for that, you need event time support. And if the windows, which are like the tumbling and the sliding window, which are supported natively by Flink, isn't enough for a use case, you can also use quite a custom window with the evictor and trigger model of Flink. That's not a big deal. Okay, so far so good. The problem with Windows is that they keep the data around. So as long as the window is not finished and hasn't been computed, you have to store the data somewhere. In case that the window is either really long or the elements are really large in size, it might not be feasible to do so. And when it comes to counting, we don't really need the information of the events, right? So the only thing we need is to know that there was an element, and then we have to increment a counter along by it, for example. So to do it a little bit more memory efficient, we can create a stateful mapper, which simply increments a counter value every time it sees a new element. That's a different way to implement a solution for this problem of counting impressions. How would that look like in the API? Well, the only difference to the previous program is that instead of a sum operator, the sum method, we call the map with state method, which takes a function which has 2 parameters. First parameter is the event data, so our tree. The second is the state, which is a long, which you can use within the function to calculate the current count value and where we increment it to reflect the new one. That is quite easy. However, what happens if, well, the machine on which our operator runs crashes? Then our data is lost, right? And henceforth, we are counting incorrectly, which is not what I've said before, that Flink gives you exactly one processing guarantees. So there has to be some mean to recover from a failure like a machine outage, for example. And what we basically have to do, or what the system has to do, it has to store your state somewhere. And what this basically means is that the system has to be capable of drawing a distributed snapshot from a parallel data flow, including the operator states. Since Flink uses a continuous streaming model, which means that all the operators of your data flow are online at the same time, and the events are continuously streamed from one operator to the next operator once they're ready, it's not so trivial. So you somehow have to synchronize the individual operators and to tell them when to take a snapshot, so that the complete snapshot, so every operator gives you a consistent snapshot. How this happens in Flink is by introducing barriers or markers in the streaming pipelines between the operators. Here it's important to note that these barriers cannot overtake and cannot be overtaken by the elements, which are streamed before and behind the markers. This means that whenever an operator, let's say here's our stateful mapper, sees this marker, it knows that it has now seen all elements up to this point. And it can now take a snapshot of its state, and if all other operators behave similarly, the overall snapshot will be consistent. It can be recovered. It can be used for recovery. And in terms of processing guarantees in the streaming world, which are at most ones, at least ones, and exactly ones, with this asynchronous barrier snapshotting algorithm, how we call it, we can guarantee all of these three guarantees. It is, well, first guarantee, the at most ones, actually, well, not so useful in real-world problems, because it basically says that you might see an event in an operator, but, well, if it crashed, then you might not see it as well. So no guarantees at all. It's easy to realize. A slightly harder guarantee, the at least once, basically says that you will see every element once. But in case of a failure, it might happen that you see that you process some of the elements multiple times. And exactly once means basically that in your final result, every element will be accounted for exactly once. And that is the hardest one actually, but also the most important one. However, as a user, just to know, usually the at least once guarantee is for most use cases sufficient, and you would always use or choose the weakest guarantee to minimize the overhead. Okay, what does this checkpointing now mean for our stateful mapper? Okay, well, if we take a look at it, it looks like before. The only difference is that by enabling the checkpointing mechanism, the system inserts these barriers into your input stream. And what the operator does is whenever it sees such a barrier, it will take the value it has currently stored in its count value and write it to some state backend. In our case, it is HFS here. But this state backend is configurable, and but currently we support file systems, well, including HFS, memory state backend, and we are currently working on a RocksDB state backend. So for your user function, or for the implementation of that, it's completely transparent. So you don't have to bother about what's happening behind the scenes. Okay. Now let's take a look at the performance and what's the impact of this checkpointing mechanism has on the overall performance. When we talk about performance in the streaming sector, we always talk about, or have to talk about latency and throughput. These are the two important measures. Due to the fact that Flink has this continuous streaming model, where the operator is always online, and once an element has been processed, it can be sent to the downstream operators. It can achieve really low latency. But to be precise, in order to also achieve the throughput rate, the elements are not directly sent to the downstream operators, but they are buffered before. And they are sent to the downstream operators once the buffer is full, or once a buffer timeout has occurred. And with this buffer timeout, we basically have an upper value for upper bound for the latency you can expect. And in order to show you that, we run an experiment where we had a simple input stream we read from Kafka. We grouped on some key and counted the elements in each group. And we ran this experiment on a 13-node GCE cluster with, I think it was like 4 cores and 15 gigabytes of RAM. Yeah, there were the specs. And we measured the latency, which is the green line here, versus the aggregated throughput. And that we did that for varying sizes of the buffer timeout. So starting from 0 to 100 milliseconds. As you can see, with an increasing buffer timeout, the latency also increases because the elements stay longer in the buffer, and this is more likely that the elements are sent to the downstream operators once the buffer is full, the longer the buffer timeout is. However, the upside of this is that also the throughput increases. So as a user, you can use this buffer timeout to tune your system either to having lower latency or higher throughput. Next, we wanted to know what's the effect of the checkpointing mechanism on the overall throughput. What we did is we fixed for the same job, where we have a grouping, which means a network shuffle. We fixed the buffer timeout to 50 milliseconds and computed once the aggregated throughput without checkpointing, and one with exactly once, so with checkpointing enabled. And as you can see, for the without checkpointing, we could achieve, I think it was like 87 million events per second. That's what we could process. And with the checkpointing or the exactly once processing guarantees, we had 82 million events. So by sacrificing approximately like 4% of the throughput, you achieve exactly once processing guarantees, which is a really great result. Okay, so much for the performance. Now let's take a look at the future and what's going to happen within the next month. So now I've talked well, about counting. Counting means like having a long value, which is not really big. However, it happens that the state of operators can grow quickly, really large. For example, if you have an NLP model in your operator, then it can easily be several hundred megabytes. And writing this model to some disk to store it can take some time. And with the current implementation, the problem is that the writing the data out stores the operator, and also the processing of incoming events, which is for stream processing, well, kind of prohibitive. So what we are currently working on is asynchronous snapshot, so that the processing of the events can continue while storing the current state to some persistent storage. Additionally, we've seen, as I said, some of the state can be really large, so that it cannot be kept on the heap. So what we additionally work on is out of core state, so that once your state grows so big that it can't be held in the memory, that it will gracefully spill to disk, where it can also be retrieved again. That's one big thing we're working on. Next, we've noticed that during the streaming job, the load is not always constant. So what you usually do to meet your SLAs is to provision for the maximum input you can expect. However, this means that most of the time you will waste some resources because you don't receive this high input rate. So what we want to do, or what we are currently implementing, is dynamic scaling in and scaling out, which means that whenever Flink detects that there's a slow operator, like for example, let's say here, then it will spawn a new operator so that the load is more evenly distributed across all operators, and that the SLAs can be kept again. And the same works the other way around as well, that whenever an operator idles too long, it will be the DOP of the topology will be decreased so that you don't waste any resources. However, that only works if the architecture is capable of requesting new resources, which means new machines, and releasing these machines from a resource manager. And currently we support Yarn as such a resource manager, where we have this feature that when the job manager sees, okay, I need a new task manager to deploy some more tasks, I will tell my resource manager, and the resource manager will give me that. And also, when the task manager is idle, it can be released. And this will also be part of the new Mesos integration, which will also happen in the next month. Okay, last but not least, there's also some other good stuff going on with declarative queries. Currently, we have contributors working on stream SQL, which will basically bring SQL to the streaming world, so that you can use your SQL knowledge also with streams. And we're implementing complex event processing, so that's really easy, not touching too much code, to detect complex event patterns in your streams. For example, if you want to detect like suspicious behavior in your network, you might define some rules, and this could be used to detect intrusion, for example. And with that, the only thing which is left now is to conclude my talk. I hope you've enjoyed it. If you got excited about it and want to stay tuned, you should check out Flink.Pache.org. There you will also find the mailing lists to which one can subscribe. And take a look at the code, which you find on GitHub, or follow us on Twitter. And yeah, thank you very much for your attention.
When snapshotting on the local disk, how do you ensure all colors?
With local disk, of course, they don't have fault tolerance. You would have to save it to HFS, for example, where it is replicated.
There was a benchmark made by Yahoo. It was also looked by you that showed very less performance for Flink than what you have shown here. So how can you explain the difference?
Well, actually, the benchmark done by Yahoo measured the latency of, let's say, the Redis throughput, and the results were not bad for Flink. Actually, they were on par with Storm, which is known for having really good latencies. Actually, moreover, is the benchmark. The measurement of latency is really difficult in distributed settings because the clocks might not be synchronized between the machines. So even slight changes will disturb the results of your measurements. And the way the Yahoo guys measured the latency was basically that they had a job then they was basically a map operation or the group operation. And then they, in this operator, they made a lookup to a Redis store to do like a join operation. Like, this result, they wrote every second to some database to measure the latency between the time point when it was written and the endpoint of the window of 1 second. So, which basically means that even if you assume you have a latency of 0, then the element would arrive in the first window, but wouldn't be written to the store before 1 second has passed, because only after 1 second it was written to this database. That way, the latency measurement was kind of flawed in our opinion. And, yeah. But the overall results were so that Flink and Storm were on par with respect to latency. Throughput was not measured there.
If I have my query and then I call execute, can I change the query during runtime?
No. It's at the moment it's like think of having a static query where the data is piped through and then yeah, I mean with the API or with if you specify it as a SQL query, you construct a data flow graph which is compiled to some internal structure which is then used to execute it, the specification distributed.
I want to move away from relational database to a more even sourcing model with streams. Can Flink help to track back transactions?
Flink allows to within Flink you have guarantees that there won't be data lost using this checkpointing mechanism. However, once you cross the border from Flink to a different system, they have to interact. I mean, the system has to respect these checkpointing notifications to make sure that no data is written twice, for example. If you do that, then yes. But you have to implement it for the specific connector you're using there.
One last question.
What are the different ways I can connect to Flink? I'm guessing it's TCP, but do you speak any other TCP protocols or any other things?
Yeah, what do you want to connect with Flink?
Say like some type of IoT protocol, MQT or something like that.
I mean, the way to connect to Flink as a client is you have use Akka internally, so you have like can basically send Akka message to it. But usually what you usually do to ingest data is you have connectors, and there's a wide variety of actually all Hadoop compatible stuff which is supported. I mean, all Hadoop input formats can be used, but there's no other way. I mean, that's not true. You can use the REST interface to request some metrics, but there's no other way to interact with the system yet, like other protocols. Not yet foreseen.
Why shouldn't I use Spark Streaming?
Well, you shouldn't use it. But the thing is that they use different. The concepts are different. Spark uses mini batches to simulate streaming, which might be enough for some use cases. However, what you basically do is you don't have such flexible windowing semantics as with a continuous streaming model. That's one reason why you think that the continuous streaming model is superior. And because of this mini batching, you have really high latencies. So if your use case which you want to solve requires low latencies, then it's almost always not possible to do it with Spark, for example.
Take the rest of the questions offline, please.
To answer the question on IoT, and also the same with Flink, is you have a socket connector, for example, of Spark String, on a Flink string. You can listen for a socket.
Yes, that you can do.
And the difference, for example, with Spring and with Flink from Spark in this case, you will receive the message processed immediately as they go inside. And this will be a big differentiator compared to Spark.